first assignment, I guess, is what happened here. So today we'll be talking about just the beginning of computer animation, and in particular talking about a technique called skinning, which is used up and down the graphics pipeline to make our favorite zoo of animated characters like what we see on the screen here. And this is really probably now a little closer to what you guys think of as computer graphics as opposed to the kind of preliminary stuff that we have to get out of the way the first couple of weeks here. Although you'll see that unfortunately matrices and your algebra and coordinate systems, all that fun stuff is going to come into play in today's lecture. There's no escaping it. Okay, so and then of course this is going to form the fundamentals of I think the homework assignment you have due this coming Wednesday. Yep. Right. So let's wait. What is today? Next Wednesday. Today's Tuesday. I'm sorry. Even when I say stuff that scares you guys, you still don't participate. You know, I don't know what to do. Okay, right. So before we talk about computer animation, of course, it's worthwhile to talk a little bit about traditional animation, and of course, watching these old clips of people, in this case, making Mickey Mouse, which is probably going to make our video get pulled off of YouTube. Is really impressive, the amount of work that goes into the traditional animation pipeline. And actually kind of one of the interesting things is that really the principles of traditional animation are reflected pretty closely in the way that we actually animate characters on a computer as well. Right? So in case you guys aren't familiar, roughly what goes on in traditional animation is a few things. Right? So first of all, typically you don't just, even though when you're watching, I don't know, Snow White, right, it looks like it's just one image. Of course, in reality, it's kind of composited together, right? There's the background of your scene is drawn on one plate, and then they use these very thin sheets of cellophane maybe to draw layers on top of that, because otherwise the artist's job would be extremely, extremely painful, right? They'd have to like paint the entire cute forest behind Snow White every time they want to have a new frame, and of course they have to draw 30 frames a second. Computer animation, or rather just animation before computers, was a really tedious process. Right? And so the first step would be maybe you draw, and I'm not an animator, you should talk to an animator for how they actually do this. But from a high level, what was going on, for example, in Disney animation studios, was that you would have one person that paints this nice, beautiful background for your scene that was kind of static. Right? I think all of you guys kind of know this look in Disney animation where there's one kind of flat scene and all the action's happening on top of it. And then the scene would get decomposed into these different layers, which are these thin sheets that can be kind of stacked on top of one another. And then literally they would just take a big photograph sitting on top of that stack to get the final image for the animation. Right? And there's a whole hierarchy in the animation studio of who gets to draw what, right? Like who gets to draw the cool art, and who gets the really awful job of something called in-betweening. How many of you guys have heard of this before? It's like the worst job ever. I'm so glad that I can't draw because I have no qualification for this. But roughly, the interesting expressive content, usually doesn't happen at 30 frames a second, right? It happens at a much lower frame rate than that. And so the typical way that they would do this in the animation studio was you would have somebody draw keyframes, which are exactly what they sound like, right? They're kind of interesting frames in an animation. And then you would hire, I think, people just out of art school to be in-betweeners who would draw all of the smooth motion on individual plates between those things. And so this is a pretty tedious, awful job. And I think one of the early targets for computer animation was at least helping the in-betweening people out, because that's a pretty miserable job. Yeah. And it's miserable for a lot of reasons. I mean, for one, you're basically drawing like Mickey Mouse with small perturbations, for days and days at a time. But even if you just enjoy drawing Mickey Mouse, it's still quite a tedious job because you're trying to get a smooth motion, but you have to draw all these static images in a way that perfectly aligns, right? And so the chance of making a mistake is extremely high. And so there are all kinds of different clever, essentially, developments in the animation world that made this more and more efficient. Actually, the first developments were not computerized, but rather just tricky ways to make this hand-drawn process a little less painful. So for instance here is a really interesting application of geometry. I encourage you to look. So one of the things you might see in the early animated films is the camera will kind of scroll across a cute scene. And if you think about it, right, so how did they do that? Well, before computers, they had to paint the entire scene, and it had to sit on a flat plate. right? And so in order to have the camera scroll, if you think about it geometrically, they're taking the 3D world and kind of mapping it onto the plane so that at any one camera view it kind of looks flat. And so for example here, if you stand back, is there anybody here that's really good at being able to tell what Disney movie this is from the plate? I'd be really impressed. But in any event, you can see that actually they took the world and they have to curl it in a particular way, which has to do with the camera motion, so that when you move the camera along in the scene, it actually has somewhat of a 3D effect. And so there are all these clever tricks like this to make cell animation, which is this idea of drawing lots of layers work in practice. In fact, there's no better person to learn about this from than Disney himself. And so we have a little video clip from 1957 here I thought would be kind of fun to watch a little bit of. Let's see if there's audio today.
Now, this is a different kind of drawing. It also came out of our school of self-improvement here at the studio. It is a blueprint of a piece of equipment designed to make cartoons more realistic and enjoyable. This is the plan for a super cartoon camera. We call it the multiplane camera. It was intended for use in our feature-length cartoons. You see, we decided for features. The camera needed improvement too. Actually, the pre-feature cartoon camera was fairly simple in construction and operation, and generally very satisfactory. The problem was how to take a painting and make it behave like a real piece of scenery under the camera. The trouble was we were photographing a flat two-dimensional background. So we set about making plans and blueprints for a new cartoon camera that would overcome this. The different elements in the scene were separated according to their varying distances from the viewer. This put the moon on a plane farthest away from the camera. With our original picture broken down in this manner, it is possible to control the relative speed with which each individual part of it moves to or away from the camera. But the moon remains absolutely still, and so it will always remain the same, neither growing nor shrinking in size. Since this new camera used many planes, we called it the multiplane camera.
Yep. I love the sound effects.
And here now
Wait, so we
is our same moonlight scene, the way the multiplane camera sees.
Animated films, you should look carefully. We'll see
As you can see, we finally got the moon to keep its proper distance.
Okay. Right. Let me stop that before it like zips to the next suggested film. Yeah. Right. So you can see that actually animation is one of these cool fields where people have always been pretty inventive, thinking about the different ways to cope with the challenges of just producing one of these films. And these ideas are reflected in the technology we have today. Right? So the very first pipeline we had historically for this stuff that was popular was this CAP system from Disney, which was in the late 80s. And here you can actually see what this thing looked like. And it's amazing, you know, these things. It's a cellist that just
Here at Disney Studios, some interesting experimentation is taking place with computer animation. After setting the trend with Tron, animators turned their efforts to a test based on a classic book by author Maurice Sendak called Where the Wild Things Are. The object was to make the backgrounds with the computer and incorporate classic, hand-drawn Disney character animation with those backgrounds. In this way, squash and stretch the elements of elasticity that make Disney character animation stand out from all the rest would be lost. In hand-drawn animation, the next step after the storyboard has been completed is the pencil test, a rough pencil drawing to show the action. In computer animation, that step still occurs. It's called the vector test. This is the vector test for Where the Wild Things Are, which Magi Synthavision did for Disney Studios.
This is state-of-the-art computer graphics when this tool came out.
Once the vector test is approved, the real work begins. Each piece of vector animation must be modeled and shaped. In this case, the characters were painted by computer. The whole process is like stretching a layer of skin over a wire mesh frame. Now, let's take a look at the test for Maurice Sendak's Where the Wild Things Are, which was directed by John Lasseter.
Clips that are easy to take for granted. One is how modern that clip looks, really, right? And I think one of the kind of funny things that we forget about, like if you went on Nickelodeon and you saw that cartoon clip now, I don't think you would blink. And I think one of the things that we see is that although the technology behind the scenes has changed a ton, the level of standards that artists hold has not. Right? And so one of the amazing things about being a computer graphics engineer is the amount of work that you have to do to conform to what the artist wants to see, kind of regardless of the technology. The other is, of course, the shading in here is way less complicated than what we have now. But anyway, historically, one of the earliest research papers in this area really did sort of propose this high-level idea of taking these principles of traditional animation and applying it to 3D computer animation. And this includes these ideas of in-betweening and keyframes, which we're going to see form the sort of fundamental part of algorithms that we have for animation today. Right? And so, and in fact, to go even farther than that, one of the big inspirations for the algorithms and actually the splines that we've developed in this class comes from this very famous text. How many of you guys have seen this before, this Illusion of Life book? You should go to the library and check it out. So it's really neat. It lays out sort of the basics of cartoon animation, and in particular how to expressively communicate motion and so on in hand-drawn images. And one of the really, I think, insightful conclusions that came from a little bit of introspection on the part of the people that do animation is the fact that often in these animated films, there's sort of a self-consistent physics which has nothing to do with F equals ma, right? And in fact, there are all of these kind of thematic ideas that people were using in betweening and so on to express emotion and physics that is different from just Newtonian physics, but somehow in an exaggerated fashion really shows to the viewer the interesting things going on in a scene. Yeah? So for example, one of the phrases that we actually heard in that little YouTube clip are the phrase squash and stretch, which is the idea that sort of when objects move around, they tend to smush when they elastically run into something and then stretch back out. Notice this is completely non-physical. That, like, for instance, here is a very typical kind of sequence of a ball bouncing in an animated film. And the ball actually anticipates hitting the ground, which is not a thing that balls do. But this is a thing that your brain is perfectly happy to accept as physics and sort of understand in its own self-consistent world. And in fact, in some of the early animation tests, people thought about, like, how can we replicate that for something as simple as a rigid lamp, which was probably easier to animate than a skinned object. Right? Of course, we all recognize this rigid lamp today. Another one that people thought about quite a bit is timing, right? The timing affects maybe the way that you perceive the weight of an object. Is that true? No, right? In gravity, we know that the acceleration due to gravity has nothing to do with weight. But of course, it took people a remarkably long time to get to that point in the real world, in the physics community, and animation is still behind in some sense. And the reason is that our intuition for how the world works is different from how the world actually works. And computer animation can actually leverage that to make for interesting motion. Right? And so these are the sorts of degrees of freedom that animators like to play with that we can expose, and are sort of the reason why an animation isn't just one giant physical simulation. Right? It's its own special world with its own physical rules that have nothing to do with what we actually have. Yeah? And of course, even though now we've switched to a very different look for the film, these same principles are really what's underlying what we're doing. Yeah? By the way, of course, in animation, one of the nice things that you can see here is if you're in production, it doesn't matter if you take as much time as you want to render a frame, because at the end of the day, you're just going to play back that movie. Of course, these days in video games, we have to do this at like 90 hertz, so that you also have some CPU time left over for your AI and your game and so on. Okay, so today, now that we spent a little bit of time talking about animation and some of the interesting challenges from a high level, we'll identify a few key types of animation which roughly follow what we're going to be doing in the coming weeks in this class. And then we'll talk about how to control animation, and then one particular technique for getting a physical-ish looking natural bodies, which is skinning, for putting skin on a rigid object. Okay. So let's talk a little bit about the different types of animation as they're sort of classified in the algorithmic world. Okay? So first of all, probably the one that we've talked about so far, and the one that we're most suited to approach with the tools we've developed in this class is keyframe. Right? The basic idea here is if for some reason I want to animate a bunny flying through space, I'll admit this is kind of a corny slide, then maybe I specify a few key poses of the bunny. And then the computer, rather than this poor in-betweening person, the computer's job is to generate the in-between frames automatically. And of course, in actually lecture 2 of this class, we already started developing the machinery to be able to do that. Right? Things like splines are exactly the right tools for in-betweening. And indeed, if you play with an animation tool, typically what the kind of view looks like is, there'll be, here's your 3D scene, here's your bunny, it's your first order. Got a little smile, and a wink. Anyway, so you have your bunny here, and then down here, you'll have this view, which is like, maybe, this is his joint, and this guy is his knee, or whatever. You'll actually see a spline that you can fit together for the different degrees of freedom. So that way, when you play, there's this little vertical line that moves across, and it shows you the splines in joint space and the animation at the same time. It's a pretty typical user interface. But that's only one type of computer animation, and there are many others. So for instance, there's the idea of procedural animation, where you describe a motion algorithmically. And this is still some set of small parameters that change over time, but maybe they compose together in a more interesting way. So for instance, a pretty typical procedural animation would be, I give you the time, and you give me a clock with the seconds and minutes arms in the right places. And of course, as I tick the time variable forward, the clock is animating itself. Right? There's a piece of code for how to place all the different objects there. This is different from the in-betweening style where I would have to specify a spline over the 1 hour clock telling the position of all the joints. Procedural animation and procedural modeling are extremely important, especially in sort of very large scale scenes. Right, so in fact, a lot of big developments in this area came in. What's that movie with the all the Romans that came in? And it's like 30, 24, 72. It's got a number. It's kind of 300. And right, there's this huge hordes of people storming whoever they were fighting. I'm sorry, I haven't seen this movie. And of course, animating all of these different characters running in and storming the enemy would be extremely expensive, right? And so a lot of times when you have, especially in zombie movies, because procedural animation isn't always that good, so if you're creepy looking characters, you get it for free. Procedural animation is quite important, right? And it's informed, for example, by machine learning tools, which can kind of, for example, watch you walk around for a while and then try to figure out your walk sequence from it. Yeah? And then finally, one that we'll spend quite a bit of time on in this class is physically based animation, which I think oftentimes we don't attach the word animation to this, we just call it physical simulation. But really, physically based animation is the proper term here. The reason why is that there are a lot of physics techniques in the computer graphics world which are totally garbage if you're a physicist. And again, it doesn't matter, because what we care about is the perception of physics. You see that this is different from actually capturing the Navier-Stokes equations and doing fluid dynamics accurately, for example. And so, for example, the things that we'll talk about in a lecture or two for simulating cloth and hair and so on have nothing to do with the physics of actual cloth and hair. That's really complicated. But they're enough to convince you that it looks kind of right. Yeah? Although at the same time, state-of-the-art in physical simulation, I would argue, largely is in the computer graphics literature for certain physical phenomena, where just by virtue of getting it right on the screen, you really do have to simulate it quite carefully. Right? For instance, combustion is a good example. Yeah, I believe that's a pretty popular thing to have in a movie. And really, physical simulation is pretty amazing these days. And watching these tools at work is just like a great thing to do if you're bored on YouTube. I'm going to turn off the tunes on this one. Right, so all of the clips in this video sequence here are computer generated and animated. I think in this case it's using a particle system, which is what we'll cover in our next lecture, 2 lectures from now, I forget. You can kind of tell because when the water splashes, you'll see these droplets that all come off and they're all kind of the same shape, which is usually the dead giveaway for this kind of thing. Yeah, so you feel really closely over here. Yeah. This is, yeah, so this is amazing to me. Now, do we have any experiments showing that, like, if I poured water in, it would actually make a wave of that shape? No. But do we care? No. And these are pretty convincing as clips go. In fact, I'd say the water is convincing in some of the other parts of the scene, not so much. Yeah. That scene even more so. Yeah. Right. YouTube, let go. Okay. Or here is an example where we're actually going to combine sort of the last two. Right? There's some physics and some learning here for character animation, and the end result is a character that can do things like jump and do flips and what have you. In this case, I think they have several plausible motions that they can do. So for those of you guys who remember the phrase boundary value problem for your differential equation class, that's roughly what's going on here. And you can see that the animated is our character. I love watching these classes. I could do this all day. But anyway, right. So of course, at the end of the day, animation is a tricky thing because, you know, on the one hand, we want our characters to be physical, but on the other hand, we want them to be not that physical. On one hand, we want them to obey, you know, maybe what the artist wants. On the other hand, we don't want the artist to have to spend all day keyframing. There's all these different push-pulls between, you know, different levels of detail that have to happen in a system like this. And carefully transitioning between those is something that continues to be studied to this day, and really depends on the artist, the task, and so on. But because we're typically pretty lazy, animation really is controlled by a few low-dimensional knobs. And we've already seen that in the previous lecture. For example, when we were talking about articulated bodies, right? There were just a few joint angles that control pretty realistically the pose of a humanoid model. And oftentimes those are much easier to animate than like every single point on your skin independently, right? And so the art is all about how do you carefully articulate a character, or in other words, expose the degrees of freedom that are interesting to the animator and easy enough to use. And we've already seen several examples of that so far. There's a great internet demo that I encourage you guys to play with at home, which has to do with facial expression, and where they kind of map low-level controls onto higher-level ones. Unfortunately, I just tried this before lecture, and my browser wouldn't do it, so we're going to skip over this. If anybody can manage to get it on their computer, maybe at the end of the lecture, we'll give it a try. Okay, so today, so today we'll be mostly focusing on this particular part of the animation pipeline. But like we saw at the video at the beginning of class, building 3D models is really a critical part of the process of making a scene, right? And so, you know, in this class we're not going to focus too much on art and story, so really it's this next step which is really key, right? And as we go forward in this class, we're going to move farther and farther to the right. Yeah? Of course, the reality these days is that there's a lot of feedback. It's not this nice straight line that you see here. Okay, and we've already seen one place we can focus, which is on articulated characters. And of course, we know now, at least given your nano quiz, the two kind of keywords for how you might animate such a thing. Right? One would be forward kinematics. So in the context of animation, this would kind of look like, for example, putting a spline in joint angle space as a function of time. Right? So this would tell me like how I'm moving my arms around. And then in IK, or inverse kinematics, maybe I give a spline of just 3D positions, and I force my animation system to figure out the right parameters of the system to achieve that. You know? Doing IK in a way that is coherent as a function of time is extremely challenging. Okay. So in order to have a nice articulated character, even though that might be what's happening behind the scenes, it's probably not what we want to render, right? This guy composed of a bunch of ellipsoids is not the most exciting character ever, right? And of course what we prefer is to render whatever this thing is. And so there's a little bit of an interface that has to happen in between the skeleton, which is sitting inside of this creature, and the actual motion of all of the points, which are probably some triangle mesh which is sitting outside of the skeleton. Right? And so that's going to be our task for today. And that task is called skinning. So the idea is that sitting inside of this guy really is one of these boring shapes, and as I animate the boring shape, I kind of want to drag along the more interesting body with it in a way that looks kind of physically plausible, which is a phrase we're going to use a lot in the next few lectures. Okay? And the way that we're going to do that, the key vocabulary words here is that the underlying skeleton here has a bunch of bones. These are the rigidly moving parts. And what we're going to do is bind skin to the bones. So here the term bind is referring to how the skin moves as a function of the positions of these basically line segments or ellipses. Does the basic setup make sense, like what we're about to do here? Cool. And skinning is one of these topics that can be arbitrarily complicated, right? I mean, you could imagine simulating the muscles underneath his skin and like the skin sliding across the internal workings of his body. That's actually what happens in some pipelines. In video games, there's just a formula maybe that determines this as a function of the positions, which is less physically plausible, but more easily computed. Yeah? Okay. It's important to note that like hand animation is not the only application of skinning. So another one is in Mocap or motion capture. How many of you guys have gotten to try a motion capture rig before? They're kind of fun. Yeah? So somebody, at least maybe 5-10 years ago, what would happen is you put on a big suit with a bunch of markers or ping pong balls to first order attached to your suit, which are roughly, notice that they're roughly the locations of your joint. Right? That makes the IK problem much easier to solve. And then what happens, you move around, you're acting in front of the camera, and then the camera is tracking these points in 3D, so maybe you have many different cameras around your scene, and then you use those to animate your 3D character. Okay, so this is one way to get around this kind of tedious process. Of course, there are a lot of animation studios that actually don't like this mocap procedure. This is a little bit of an infighting that happens in the animation community. Because what happens in mocap is that implicitly your animated characters are constrained by motions that you can actually make in the physical world, right? And so some animators would consider, especially the snobby ones, would consider that to be not such a good thing, right? And indeed that's the case. So for example, when I was working at an animation studio, we had a brilliant idea that we realized later was not super smart. Where roughly at the time, WALL-E was coming out, remember with the cute robot that rolls around? And WALL-E's a robot, and actually it's pretty easy to build something that looks like WALL-E, right? It's just like a giant cube with some eyes attached to the top. And so at the time, they were thinking about making an actual WALL-E that could like show up and like have a little conversation with the newscaster on TV as a promo thing. And so they thought, oh great, well we'll actually articulate our physical WALL-E roughly similar to the WALL-E in the animated film, which you can do, it's a robot, right, I mean, for heaven's sake. And then we'll just take the animation splines and put them on this guy, and now we're going to save a bunch of time because WALL-E is now articulated and moving around. The only problem is that if you look at the motions that WALL-E actually takes in this film, when you transfer them to a physical object, they're like enough to actually launch WALL-E off the face of the earth. Right? And so when you physically constrain yourself, for example, by using mocap and so on, you really are working in a much more constrained space than just the full ways that you can play with the degrees of freedom. Yeah? And for some movies, that's what you want to do, right? Like for instance, maybe you're animating like, I don't know, what is it that the kids watch? Like Thor, and he's like inside of some scene and he's throwing his hammer, but like he has to interact with other people, in which case you do want there to be some constraints from the physical world. And then maybe mocap makes sense, but for like a cute trash collecting robot on the moon, it probably doesn't matter, right? Okay, so right, but mocap technology is really fun, and actually these days, of course, your phone, if you have one of the newer iPhones, actually has a version of this that's markerless. And so here's an example where you have a character with a bunch of fiduciary points marked on their face. Here are the same points on a 3D character. It's articulating in motion. Yeah.
I was going to ask why, so if you use mocap, why does that constrain you from doing crazy stuff? Like, can't you just transfer this data into a sort of less constrained virtual version which you can stretch more?
You could, and that's the counter argument that people make is, well, you could go back and edit this. in any way you want it, but of course fundamentally you're constrained by the motions that the actor can make. In fact, there's a really funny research paper from MIT actually before my time, where one of my colleagues wanted, like, you know, I'd like to make some motions and then project them onto an animated character, but maybe that character doesn't have the same joints that I do. Right? So instead what I'm going to do is I'm going to work by analogy. I'm going to say, when I make this motion, I mean that my character does this. Right? So I'm going to give a bunch of 3D scans of myself in different poses and say these poses correspond to those ones, and now I can do mocap and try to control this character in kind of a funny analogy way. And I encourage you guys to track this paper down because they wanted to control a horse and they had some trouble with it. And so they got 2 grad students to, like, one grad student sit behind the other and they kind of like do what they do. You know, there's this video of this horse. Anyway, it's fun to look. Okay, so right, this motion capture technology conceptually is pretty straightforward. In practice, it's a giant headache to get right. You know, mocap is roughly just capturing the positions of these markers over time, and then behind the scenes you do exactly the kind of math that we've already talked about to recover the joint angles and so on. There are a lot of problems with mocap that people continue to study now, and actually, I mean, it's amazing. Every year when I teach this class, the technology is completely different, really. And so the last year, what's really driven this is your phone. And I think you'll see more and more kind of VR, AR style applications, right? One of the big complaints that a lot of actors had in mocap was the fact that they had to put on this weird suit and put all these markers on their face and so on. And of course, getting Brad Pitt to do that is quite challenging. And so one of the big pushes that people have had is to study the markerless motion capture problem, which means you just have a video sequence and you're trying to capture an actor moving around, which is extremely difficult computer vision thing to study. But yeah, so anyway, there's some really interesting examples of that here. This paper is now a couple of years old, and actually this is some of the technology that went into what's now an iPhone for the face. You know, they had that goofy feature where you could like send a text message where you like control the little turd emoji, and that's roughly what this technology went. And I like to tease my college, but that's what they use it for. But the reality is he's making a lot more money. Right, so if you guys want a good research challenge, of course, markerless mocap is a great one, and you know, in fact, here's exactly that feature being demoed last year. It's very excited people. I don't think this was enough to sell a bunch of iPhones, but it was an interesting concept. Yeah. Okay. Right. And this technology really has been used to great effect. And one of the interesting challenges we're not going to talk about much in this class is how do you, for example, if I want to control Davy Jones. You know, Davy Jones has like things coming out of his face and all kinds of weird things, but his basic motion is actually controlled by a human character you see here. So at the end of the day, not only do you have to capture his motion, you have to composite it into a full scene, which is itself an interesting challenge. Yep. In fact, every once in a while, if you have bad luck, maybe the video, you see like a little bit of his mocap suit. Have you guys heard of rotoscoping? It's another terrible job in an animation studio, where like all of the technology has failed. We can't figure out how to get rid of these few pixels and all these things. So you just hire an artist to go through all of the frames in the video sequence. No. Aren't you guys glad you're in computer science? Okay, right, so as our last topic today, although this is the majority of our lecture, we'll talk about how to actually do skinning in practice, which is what's on your homework. And of course, this is really critical in any video game you see. You'll see this technology. In films you will too, but it's probably more physically based because they can afford to do some more expensive stuff. Okay? So we already know how to animate the bones now, right? Maybe we have keyframes and joint angle space. And our job now is to put that thing inside of a mesh and move the mesh along with it. Yeah? And that's this process of mind. Okay. And so today we'll talk about the most popular technique, which is something called skeletal subspace deformation, SSD. Not to be confused with solid state drive, or like I'm sure many other SSD acronyms. Or we call it skinning, or vertex blending, matrix palette skinning, linear blend skinning. All these things are the same. Linear blend skinning is the one that I'm familiar with from the geometry. And we'll see that it's a total hack, and it's total garbage in a sense, but it works depressingly. Okay. Right. So in SSD, every bone has a deformation, and what we're going to think about is that, like, around some bone, roughly the skin around that bone is deforming rigidly moved with it. Right? So if I put myself in some rest pose and I just look at the stuff that's nearby in the skeleton, and I move that part rigidly, all the stuff that's near it is going to move with the same rigid motion. Right? And so the big challenges are going to happen right at the interface between these different rigid moving pieces. So first of all, what if we ignored that? What if we just said every vertex on my skin is just going to inherit one of the transformations from the bones? Right? So every bone, has its transformation from rest pose into some other pose, and there's just some array for every vertex on my skin. So this skin is controlled by that bone, right? What do you think will happen? In particular, let's say my rest pose is like this, and I bend my arm. What's my elbow going to look like? It's going to have a hole in it. Right? Because this part's moving rigidly with this thing, this part isn't moving at all, and now there's this big giant triangle that stretches across. Yeah? So that's not so good. And that's really the problem that we're trying to address. That your skin is mostly rigid, except at the joints where we're trying to prevent this weird stretching. And so the trick that people do in SSD is they say that I'm going to allow my skin to be attached to more than one bone at a time. And of course, sort of, this really is what happens physically, right? That, right at your elbow, the position of this point here is determined by the motion of both the upper and lower bone attached to it. Right? And so in particular, what we're going to have is that we're going to say, well, I could move this point with my arm here. And I could move this point with my upper arm here, which case it didn't move. And I'm just going to average those things together with sort of smoothly varying weights that vary along the surface. Right? That's the high-level idea of this trick. So what you need to be able to use a technique like this is something called skinning weights. I love automatic computing of skinning weights. Is a really fun geometry problem. Take my class in the spring and we'll talk about all kinds of cool quadratic programming ways to solve this. But for now, we're going to see that an artist just painted onto the surface saying, like, this bone depends roughly on this part. Yeah? Coming up with algorithms for doing this automatically is a challenging thing. But the idea is that all of the colored triangles here are just attached to a single bone, and then it's just this black stuff that we have to deal with. Does the basic setup make sense here? And in practice, that really is what goes on. You have this you have this sort of big array where every row is a different vertex on your mesh, and every column is a different bone. So every row sums to 1, and that's sort of like the influence of all the different bones on this vertex. These are called the skinning weights. So here's one example. Here's another. You notice that basically the skinning weights are just constant, and then some transition, and then constant. Okay. And so in practice, they don't look quite like this coarse. They look something closer to what we see here, right? That red means 1, yellow means 1-ish, black means 0. And if you take the sum of any row of that matrix, it's going to sum to 1, right? Because you'd like it to move with some bone completely, right? If it didn't sum to 1, it would be kind of weird. And so we're going to use the notation Wij to say that this is the effect of bone J on vertex I. That makes sense? That's that big matrix I was just talking about. And so if Wij equals 1, what that means is if I move this bone, then that vertex just goes with it. Okay. So these things are called skinning weights. And typically you want your weights to be non-negative, right? Because otherwise you can have something weird like I bend my arm, my elbow goes out. Right? And you'd like them to sum to 1 because you do expect there to be 100% influenced by the set of bones. Yeah, that's what that's saying. Any questions about our setup so far? And really these skinning weights tend to be just designed by artists in animation. There are a lot of times in graphics where like what's essentially a math problem is solved by an artist manually. And a lot of our research job is to try and kind of address that gap. Okay. Typically, by the way, you limit the number of bones that influence a vertex. Does anybody intuitively see why that might be? Yeah?
There are only so many bones that are a certain joint.
Yeah, like chances are my right arm doesn't affect the position of my left elbow. Right? And so if we're willing to do that and it makes our computation a little bit faster, I think that's a reasonable reason. Yeah? Okay. Right, so the Y here is typically you just don't need that many. Space is going to be a big issue on your GPU, right? Because every single vertex is going to have skinning weights. Right? So if you have to have a bones by vertices matrix that was dense and all the weights, that would be quite an expensive thing to keep around. And so in practice, we will just have some fixed number of pairs per vertex. Okay, so our question really is, how do we actually position vertices? Right? So I move a bone, and I want to take my skin with it. So the basic idea here is we could transport every single vertex with every single bone. You see that? I could say every single bone has some transformation from its rest pose into its final one. And I'm going to take every single vertex on my mesh and just like move it. Right? So I get a bunch of different copies of my character that are moved in different ways. Right? Conceptually. Algorithmically, in my code, I'm not going to actually do that. But if I did, then what I could do is just use the skinning weights to blend them all together. Does that make sense? So in other words, I get this big pile of, for every vertex, I have like a bunch of different positions that say, if this vertex were to move with bone 1, it would be over here. If this vertex were to move with bone 2, it would be over there, and so on. And I take all those positions and I combine them together using the skinning weights, so the linear combination. Okay, so in math notation, this looks something like this. So if Tj is the transformation of bone j, right, then I can make this big pile of vertex positions Pij prime, which is Tj applied to each Pi. Right? And at the end of the day, I'm going to average these things with the skinning weights. Any questions about our setup here? You're going to actually code this on your homework. Okay. Cool. So what does that actually look like in practice? So let's say that our bind pose is like this. This is the first order of straight arm. Right? Bind pose, by the way, is the pose in your kind of default skeleton. Yeah? And we're going to say that I have this vertex here, right at the interface between bone 1 and bone 2, and I'll get 50% of this position from the left guy, 50% from the right. So now I take my arm and I bend it. This model doesn't account for stuff like muscle pulls, right? This is just moving things rigidly. So it's a good approximation of my arm for some of you guys maybe. So anyway, when I bend my arm, actually, when we look at P naught, right? Then the bone 1 says it should move to the left. Bone 2 says it should move to the right. See that you can think of these like two different rectangles that are glued together. So the output position is just the average of these two guys. Is this always a good procedure? Where could this go? In fact, where could it go wrong in this image? Yes.
The inner head?
Yeah. So think about what happens in the, what do you call this? His elbow pit? I don't know. The other part of his elbow, the inside. Right? You can even see here, right? These two things intersect, which physically makes no sense at all. And now we're going to average these positions. If you're lucky, maybe they don't intersect anymore. But it could be the case that he bends his arm far enough and his arm actually makes kind of a loop in the interior, right? There's nothing saying that this thing can't intersect itself. And indeed, for this specific example, what you get is that his elbow kind of bends in toward itself a little bit. And so actually, many of you guys have probably seen this in video games in the 80s and 90s, right? Characters, as they bend and move around, when their arms bend in, like somehow something weird happens and mass disappears. This is even worse when you twist, right? It's kind of like a candy wrapper. When you twist, your arm will just shrink in on itself, which is not so great. And there are all kinds of ways to get around that we can talk about later. Right, so let's add a little bit more, and then we'll be able to fill in our algorithm. So first of all, there's a phrase that I think I've already been using a bunch, which is called your bind pose. And this is the idea that, you have to have some pose for your 3D model to start with, right? Like somebody actually made this character, and he was standing in some pose, right? Very typically, your bind pose looks like that, because it's sort of unambiguous where all of the points on your body are. And you kind of want to separate the bones from each other as much as possible in the bind. And so for your bind pose, you actually need two things, right? You need a triangle mesh, which is the thing that you're going to deform. But you also need to figure out how to embed the skeleton within the triangle mesh. Right? There's a set of kind of default transformation parameter so that I can put all of these points in 3D. Right? So in other words, I have a map from my skeleton hierarchi into the coordinates of the bind pose. Right, so the undeformed vertices, those are what we're going to call Pi. And this is in some sense a global coordinate system, at least for the 3D shape. Okay. And now, what do? I bend the arm. And if you think about it, something kind of funny has to happen, right? Because when I bend my arm, I'm specifying that angle in elbow space, right? So if I have a position of the outer skin in 3D, I have to write that position in elbow space, transform the elbow, and then undo it again, right? This is going to sound just like our previous lecture, right? Okay, so that's essentially what we're going to do here. In other words, this transformation TJ is a little bit sloppy, right? It's encoding a composition of things. Okay, so right. TJ we can think about as being in the local bone system, right? So in other words, if you think about going down the hierarchy, this gives some rest-pose transformation. And so actually we'll change our notation a little bit and give those B's, right? These are our constant. Because we're going to need two transformations to use that, one for rest pose and one for deform. Okay, so this is going to be BJ, which goes from local bone coordinates to global ones. And how do you think I get that in practice? Well, it's exactly using the algorithm we talked about last time, right? I go down the skeleton hierarchy, where essentially I set all my parameters to 0, and I just read off that matrix as I do that. Okay. And so, right, so this thing is just concatenating all of our hierarchy matrices. So now I animate my model, and I change my transformation to some t, right? Which, if you remember our last lecture, right, as I go down the hierarchy, what I get is a matrix that goes from my local coordinates to global ones in the deformed pose. Are you with me so far? I get this stuff backward, which is why I'm going to keep repeating. Okay. And this also is just the concatenation of hierarchy matrices. Right? And so at the end of the day, what do I have to do? Well, I have to take the vertex in the pose of the original guy, write it in the pose of the bone, deform the bone, and undo it. And that, ta-da, is this expression right here. Do you guys see that? So this is like a position in world coordinates in 3D. This matrix B is what I got by traversing the skeleton of the rest pose. And remember that the matrix I get when I do that goes from skeleton coordinates to 3D. So I need to invert it, right? Because I want to go from 3D to skeleton. Now I apply the skeleton transformation and I undo everything. Yep. And this is going to give me the PIJ parameter. Everybody with me so far? Any questions? I know this stuff is ridiculously easy to get backward. And in fact, you will get it backward. On your assignment, you'll change his elbow to go in and his arm will go the other way or something. And this always happens. Yeah. Okay. Right. So again, what this does is it maps from the bind pose to each of the different guys. Okay. So then, of course, what we have to do on the outside is just put a sum over the W's, and we're done. Yeah. Okay. Right. So a few details that we skipped over. One is how do you actually get the vertex weights? We're going to assume that somebody just painted them by hand. We'll talk very briefly about some automatic methods, but that's not really a focus in our class. And so really at the end of the day, here's our pseudocode. By the way, do the BJs change as I animate my 3D model? And it was vote yes. I was vote no. I was vote something in between. And the answer is no, right? So because that is the bind pose, right? The bind pose isn't being animated, right? And this is just the thing that goes from the 3D position to the different skeleton bones. By the way, if you guys aren't raising your hand and you're lost, you should ask a question. Okay. So let's say that I have a triangle mesh. Remember from assignment 0, you loaded in not just vertex position, but also a normal for every vertex? Should I use the same formula for the normals? No, what should I use for the normals? The inverse transpose. Exactly. Yeah, the inverse transpose of the principal 3x3 submatrix. In other words, I take the sum on the left, the upper left, and I flip it and invert. Yep. And that's exactly right. You have to be a little bit careful when you deal with the normal values. And typically, by the way, your triangle mesh will come with normal per vertex. It's not something you compute. Which makes sense because if you have a bunch of triangles meeting in a point, it's not totally clear what the canonical outward direction is, right? This is a bit of a choice thing. Okay. Right, so at the end of the day, notice that the weights and the bind pose are all constant over time. The only thing that changes are these t's. And so that's what we're using to compose our transformations together. And in practice, on the GPU, what we implement is something called a vertex shader, which is a little bit of a misnomer, right? This is just a thing that gets applied per vertex to compute its position, right? And so these, essentially, if you're totally bored, you don't care about where that came from, these are the formulas that you'll implement on your homework. But of course, that'll get tangled together with the fact that you're walking up and down this hierarchy of transformation matrices to deal with the skeleton underneath your creature. Okay, so if you think about it, this works really well for translating objects, right? Like just rigidly moving them. But rotation, is there any reason why this should be a particularly good rotational model? Not really, right? So remember, to give a concrete example, remember that our 2x2 rotation matrix is something like this, right? It's cosine theta, sine theta, minus sine theta, cosine theta. Yeah? So first of all, what is when theta is equal to 0, I get the identity. So this is theta equals 0, and theta is let's say pi over 2. So 90 degrees. All right, a little bit of trigonometry. What's cosine of 90 degrees? Everybody, 1, 2, 3. 0. Ah, there we go. Some participation. So we get 0. And what's sine of 90 degrees? 1. Okay. Oh, 1. Cool. And in fact, for fun, let's do theta equals 180. So my character does the hokey pokey, turns himself around. What's cosine of 180 degrees? 1. Sine of 180 degrees? 0. What did I do wrong?
Cosine 180 is minus 1.
Oh, yeah, thank you. Sorry. Okay, so what if I have two, let's say that I have my arm, and I bend it 180 degrees, so in other words, I kind of just bend my arm straight up. What's going to happen to my elbow? Well, remember that roughly what I'm doing is I'm just taking these two matrices and averaging them together. What's the average of these two matrices? 0. Is 0 a rotation matrix? No. Right? And that's where SSD is kind of a hack, right? Because what we're doing is maybe we're taking different rigid motions and averaging them together, but the average of two rigid motions arithmetically is not rigid. Yeah? And that's why this thing is completely non-physical. By the way, this has a lot of implications. So one of the tasks that everybody thinks is easy, but turns out to be hard with splines, is let's say that I want to use a spline to interpolate camera positions. Right? So I have some dramatic, scene, and I want my camera to swoop through it as I animate. Right? My camera is probably specified by position in 3D space, but also orientation. Right? And making a spline in orientation space is extremely challenging. And doing it in Euler angles can cause really crazy artifacts to like flip over and stuff. Okay. And so in practice, you see that. So here's an example of a character. If you bend his arms, you get like a little Gumby artifact, which that you would kind of expect and maybe be okay with. But if they twist, the arm actually shrinks, and if they twist 180 degrees, it collapses to 0. Yeah? And so there are a lot of different ways around that. One of the kind of magic tricks is to express rotations not as matrices, but as quaternions. That's not something that we'll cover for now, but it's just a different expression of a rotation. But it turns out not to be rigid, but at least it takes rotations to rotation, which is a start. Okay. There are all kinds of cool optimization problems for finding the weights. This paper is out of date. If you're interested in this for your project, come talk to me. And in fact, there are even algorithms out there for automatic rigging. So maybe somebody not only gives you just one rest or like bind pose of a 3D character, it actually gives you like a few different places that are like examples of how they move around. And then from there, you might ask a computer system to actually infer the positions of the different bones that are controlling the character that the artist put in different poses. The reason you might want to do that is it might be more intuitive for the artist to actually just model 3D shapes than to actually embed a bunch of like cosines and sines in this form. Okay, so for example, here is one of the first automatic rigging algorithms where they take kind of a generic dog skeleton and a 3D dog character, and try to match them together in assorted ways. And the results can be pretty convincing. So here's, oops, that's not that one. Here's an example. Let's see here. Ilya, by the way, is a former MIT grad student and a buddy of mine. Right, so they have some basic kind of walk cycle for a skeleton, and what they'd like to do is say, well, since I have that walk cycle for this generic skeleton, now that I made this character, can I just stick that skeleton in there and automatically make it walk? And you can see that essentially there are a lot of characters that walk very similarly. Right? So there's a lot of opportunity here for things like transpose. And indeed, in this particular discipline, you can get really creepy videos. So here they're controlling, trying to see if there's an easily spotted artifact as well. Yeah, so one of the big issues in this particular discipline, in fact, this is the character you'll animate under homework, is that, like, for instance, a lot of these characters are self-intersecting because, like, you're very unlikely to have one skeleton control a bunch of physical things, right? But roughly you can, and as a starting point, that's an okay thing to do. Okay. And indeed, there are a lot of interesting automatic skinning methods out there as well. So this is one of the classic ones that's willing to play on YouTube. Right. So I think the basic idea here is you have some examples of different motions. And then you can animate all kinds of objects moving, with roughly the same. Okay, guys. So with that, that's all we got today. So your main takeaway should be this SSD algorithm, which is all about just averaging rigid motions, where your weights come from a few fixed weights that are functional on the surface. And even though this isn't totally rigid, the first order kind of is, and it allows you to take a bunch of discrete poses, or equivalently, motions, a rigid motion of the skeleton, and transform it onto an actual moving object, or a lady that's waltzing by herself. So with that, I'll see you guys on Thursday. So get started on your assignments. You've got everything you need to do your assignment now. So now you've got plenty of time to get started. And you can watch weird